Solar eruptions are energetic events that send high-energy radiation and charged particles through interplanetary space. However, if one of these eruptions is directed towards Earth, satellites, astronauts, and electrical grids can be negatively affected. I'm Avallone, a graduate student at the University of Hawaii Institute for Astronomy. In this Aloha brief, we're going to review a few key points from my recent paper, where I discuss how certain properties of solar active regions, which are a primary source of solar eruptions, can help us better understand the conditions in which solar eruptions occur. To start off, active regions are rooted in sunspots and host strong magnetic fields that can be described by a flux rope, a tube-like region of space containing a twisted magnetic field. Like all evolving magnetic fields, flux ropes are current-generating structures and contain direct currents, which connect active region magnetic polarity centers, and return currents, which surround and oppose the direct currents. It's a well-known fact that free magnetic energy associated with these currents drives solar eruptions, but it's unclear how well these driving electric currents are neutralized. An active region is considered neutralized when the ratio of direct to return currents in each magnetic polarity is close to 1. The degree to which active region currents are neutralized has been debated for several decades. While theoretical studies have suggested that the average net current density of active regions is 0, more recent numerical simulations have shown that non-neutralized currents emerge alongside the development of substantial magnetic shear along an active region's polarity inversion line. In this work, we build off these previous theoretical studies and a pilot observational study by Liu et al. 2017 by analyzing a sample of eruptive and non-eruptive active regions in the SHARP dataset from the Helioseismic and Magnetic Imager on the Solar Dynamics Observatory. We started by calculating the electric current density of active regions from vector magnetograms. From these maps, we determined the ratio between direct and return currents in each magnetic polarity. By doing this for our sample of 15 flare active and 15 flare quiet active regions, we can compare how well correlated the degree of current neutralization is to flare productivity. We compared the degree of current neutralization between flare active and flare quiet active regions and found that the degree of current neutralization differed between these two populations at a 90% confidence level. We also compared the degree of shear and found that flare active regions had higher degrees of shear than flare quiet active regions, also at a 90% confidence level. We additionally focused on examples of flare active and flare quiet active regions to see if we could find other trends within the two populations. For flare active regions, we observed that the current density maps form coherent current ribbons around the polarity inversion line. This indicates the presence of a coherent flux rope, which is a necessary condition for eruption. We do not observe the same trend in flare quiet active regions, where the positive and negative currents are more evenly distributed. Finally, we analyzed different contributions to systematic uncertainty in our results. We started by comparing the region selection method we used to compute the degree of current neutralization to the region selection method used by Liu et al. 2017, who computationally determined which regions of the active region magnetic field contributed to flaring events. To save on computation time, we used the entire cutout from the SHARP dataset and isolated strong magnetic fields using a threshold of 200 Gauss. We found that our method decreased the measured degree of current neutralization by a factor of 2. However, we don't expect the difference in region selection method to change the overall trends observed between flare active and flare quiet active regions. We also analyzed the effect of binning on our measured degree of current neutralization. We measured higher degrees of current neutralization when the magnetograms were at a lower resolution. This is consistent with the results in Georgia et al. 2012, who found that decreasing the magnetogram resolution increased their calculated net current. For the flare quiet active region we analyzed, the current stayed neutralized even when the resolution was decreased. Therefore, the source of uncertainty does not change our conclusions. By measuring the degree of current neutralization for 30 solar active regions, we determined that this parameter is a good proxy for assessing an active region's ability to erupt. For more details, check out the paper posted on arXiv. To learn more about the work going on here at the IFA, check out our YouTube channel or follow us on social media at UHIFA. I'm Avallone. Thanks for watching.